All right, we're now talking, we're still in chapter 4. We're going to talk about angular motion, or uniform circular motion. So for example, here I have a wheel spinning. And so as the wheel spins here, each part of the wheel is rotating around the center. Okay? Now if you imagine a part on the outside here, it goes around until it hits the top. So it's done one revolution. Okay? But a part on the inside does one revolution in exactly the same time. The whole wheel rotates with the same period. Okay? So in physics, we got to talk about period. And period, we use capital T for period. Why? I don't know. It's just, we do. Okay? So the period is how long it takes for a point on it to go all the way around once, so to create one revolution. And so the period, if we're going in uniform circular motion, which is what we're talking about right now, meaning that the speed is not changing as it goes around, then we can use our same distance. This is equal to velocity times time. Or in this case, we're solving for time. Time is just distance over velocity. Okay? So we can say time, or the period, is equal to distance, but the distance now is equal to the circumference of the circle, or 2 pi times the radius, divided by the velocity. So it's 2 pi r over how fast that point is going around. But we have to be careful here, because when we draw this, here's my wheel spinning around. Follow the spokes here. The velocity vector, it's going this way, is always going to be perpendicular to its rotation motion. So when it's over here, this velocity vector is down. When it's over here, the velocity vector is that way. Velocity vector is this way. So the velocity vector is continuously changing directions, even though it's not speeding up. So as it goes around, its velocity will be changing directions all the way around. But if you look at a point inside here, on the spoke somewhere, it has less distance to go around in the same amount of time. So the period has to be the same, but the circumference is different, which means the velocity is less. So a point closer in here has a lower velocity. All right. So that's the period. Now let's talk about angular variables, because this is angular motion. So normally we measure distance that we travel in meters, right? It's a length. But for a circle, that doesn't make any sense. You don't measure how many meters it goes. You measure how many angles it goes. So we're going to measure the distance in angular measures as theta, but we're going to do this in radians. Now there's a reason we do this in radians. We do everything else in degrees, but we do this in radians. Radians makes for a very nice unit because, I'm going to redraw this here. A radian was designed so that what you're doing, here's my circle, here's the radius, is we're just mapping the radius around the outside of the circle. So if I took this distance here and I wrapped it around, that'd be 1r, 2r, 3r, 4r, 5, 6. It actually takes 2 pi r radians to go around the outside. So we're just mapping the radius onto the outside of the circle. It makes perfect sense when you think about it. Now you probably weren't taught that. You're just taught this is the unit radian, but it actually makes more sense in terms of circular motion. So if you imagine our circle is spinning this way, after a given distance of time, or a given amount of time, it has rotated an angle theta, or so many radians per second. That is going to be our speed, or what we call our angular velocity. And we're going to call that omega. It looks like a W with a little thing on it. And omega is how far it goes in a certain amount of time. Okay? And then we also have to have our acceleration. And we actually have two different accelerations going on here, but we're going to talk about what we call our tangential acceleration. This is the acceleration that speeds it up, makes it go faster. So we call it our angular acceleration. And we're going to call that alpha. Okay? Now, the good thing, and the reason we use, let me move that over a little bit, that we use radians is because it makes a lot more sense. Our angular velocity, our distance is in radians, so our distance in radians per second is actually our angular velocity. So omega is in radians per second. And alpha is how fast you're changing your angular velocity. So this is just going to be radians per second squared. Now why do we use radians? Because there's an easy conversion between radians and our regular units. So if we wanted to know the distance, like the arc length here, to go across here, and I knew what theta is, S is just equal to theta r, where S is the arc length. So if I know how many radians, I just multiply it by the radius. That tells me exactly how far it is. Omega, in terms of velocity, well, V is just equal to omega times r. Because omega is radians per second here, right? Well, we know how many radians there are per radius, or essentially you have meters per radian. The radians cancel, you end up with meters per second. So V is just equal to omega r. And the same thing for angular acceleration. The tangential acceleration is just equal to alpha times r. So as long as we do these in radians, radians per second squared, the conversion to the units that you're more familiar with, acceleration, velocity, and distance, is a very easy conversion. All right. But go back to here. Here's our period. Well, if we know V is equal to omega r, then we can rewrite this equation. We can say, oh, the period is equal to 2 pi r over V, but V is equal to omega r. Those r's cancel, so this is 2 pi over omega. So we can write this like this or like this. Those are equivalent. Notice also about omega, the nice thing about omega is, remember, V changes how far out you are. The velocity is the farthest at the distance greatest radius. It gets shorter as you get closer. Omega, it doesn't matter. Radians per second, they all go through 2 pi radians in one period. It doesn't matter where you are on the wheel. So on the whole wheel, they all have exactly the same angular velocity. Everywhere on the wheel does. All right. So now we have our periods and we have our conversion. We can also then say that what is making this change? So for example, going back to here again, remember the velocity vector over here, V, is this direction, but the velocity vector up here is this one. If we're going at a constant velocity, then all we're doing is changing the direction. And if we're changing the direction, then there has to be an acceleration, but the acceleration can't be in the direction of velocity or it would speed it up. Can't be opposite the velocity, it would be slowing it down. So there has to be an acceleration, and that acceleration has to be towards the direction of curve, or we call this the centripetal acceleration. And it's that centripetal acceleration that makes it go in a circle. And so that's why we have to have t, which is tangential acceleration. Remember, this is what's speeding up or slowing down the wheel. If the wheel is going in constant circle, same velocity the whole time, it still has centripetal acceleration. And centripetal acceleration is equal to v squared over r. Or we can rewrite this, because we know v is equal to omega r, so this becomes omega squared r squared over r. But notice that r cancels, and then centripetal acceleration is just omega squared r. So every time you have an object that's rotating, you have both the centripetal acceleration, and if it's changing speed, you have tangential, but you always have a centripetal. Let me show you another example here. So, I have my tennis ball on a string. As I spin this in a circle, what is making the ball go in a circle? Well, the only thing making the ball go in a circle is the string, right? If there was no string attached, the ball would go in a straight line. But because there's a string, the string creates a tension, which is creating an acceleration towards the center where I'm pulling it. And so that acceleration is always going to be perpendicular to the velocity vector. Because I'm not speeding up, I'm not slowing it down, all I'm doing is changing direction. So centripetal acceleration is always perpendicular to the velocity vector. Now, that's very easy to see when you're in a circle, but we can have motion where it's not circular motion, but it's still making a corner. What if you were making a corner like this? Every time you make a corner here, the object, the velocity, has to change direction. So even if I'm doing it at a constant speed, it's changing direction. That means there has to be a centripetal acceleration every time it changes direction. This one would be up to curve it to a new position here. So just remember, sorry, this is the velocity vector, centripetal acceleration would be up. And then it changes to down again to make it curve the other way. The thing I want you to get out of this is know that the centripetal acceleration is always perpendicular to the velocity vector. Okay? Yes, in this case it points towards the center of the circle, but I have a lot of students that come in from high school and they only dealt with circles and they say, oh, it's always towards the center. That's not always the case. It doesn't have to point towards the center, it just has to be perpendicular to the velocity vector. All right, we'll go to part 2.